Okay, let us start our extra extra seminar. Our speaker Ivan Kostov with the title. Which title? I cannot reproduce.
Gas formulation of integrable field theories.
Okay, interesting. Let us start our seminar. Thank you for your attention.
Thank you for inviting me. I'm glad to be here. And I understood that this is a seminar for presentation of what I'm doing, what I'm interested in, and so I will start with small introduction of what is my background, and then we'll concentrate on one problem which is interesting for me during the last years. So I spent 10 years in non-critical string theory. So I've been working on large N matrix models. And non-critical string theories. Is it readable? And so this the large N matrix model, they generate random surfaces which can be embedded in some target space, and in this way one can solve the standard lattice models, but on a random graph. And these are the ON model, or the ON loop gas, RSOS models, the 6-vertex model, and also the POTS model, but the POTS model, it's Volodya Kazakov and his student who solved it. So also matrix quantum mechanics. And during the last 8 years, I started to work on the integrability in gauge and string theories. The acronym IGST, and mainly this is this involves the classical example of this activity is an integral model which is equivalent to the large N maximally supersymmetric, that is with N supersymmetries, super Yang-Mills theory in 4 dimensions, which is conformal field theory. And it has been noticed in about 20 years ago that this conformal field theory can be considered as a weak coupling expansion of an integrable model, which is a supersymmetric spin chain. Sorry. This? There is a integrable spin chain or integrable two-dimensional model, which is quantum, of course, quantum. So this is a spin chain with non-local, no, 1 plus 1. 1 plus 1 type. You can also consider it as a world sheet theory, some kind of two-dimensional theory of scattering. But it's important that the spin interaction is non-local, not only nearest neighbors, but it has a symmetry PS 2, sorry, PSU 2, 4. So you have a no 2, 2, 4. So it's a supersymmetric. It's not solidization. It means projection to SU of 2 to 4. So this is a supergroup with 4 bosonic and 4 fermionic dimensions, and 2. No, this slash. Yes. Real format. So you have 2, 2. Yes. 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 So it's non-compact. Yes. So this is when you have weak coupling. It can be mapped. The super Young-Mills can be mapped to this spin chain. Okay, I will. And on the other, in the other limit, this is strong coupling. We have the sigma model, which corresponds to this spin chain, is the string theory. In ADS 5 times S5 space. So it's a non-compact space. You have a sphere times some revolve it, which is ADS5. So this is also this correspondence is also called the CF-ADS, DS, CFT duality. So how it works, the correspondence between the gauge theory and string theory, the operators, the gauge invariant operators, which are of type of trace. So this gauge theory involves fermions, gauge bosons, and also Higgs fields. And you have some fields as phi1, phi2, etc. L fields at the same point. And this corresponds to a spin chain of length L which each each field is yes, but okay. So you if you use, for example, phi1 plus phi2 and phi 3 plus phi4, so they are they are no, we don't take, so this field, say x, and this is y. So x square is equal to 0 because you know, the square of this the fields. Let me see. The correlate. No, it's not. This is internal. Oh no! X is just if you want z, another letter. It's not coordinate. This is an operator, which is this one. So the essential is that these operators are nilpotents, because we have psi, but not this z, not z bar. So this z bar, of course, their correlation is infinite when the 2 points coincide. But here they are composed in such a way that we don't have this problem. What you mentioned. No. There is an excellent review. I will not explain that, but this is composed in such a way that the essential is that these vectors, which are yes, we prepare our fields in this way. Yes. Yes, we get null vectors with this complex combination. So they're 2-point functions which are proportional to the scalar product are 0. So we can choose the polarization in such a way, polarizations that they are. Yes. So if we choose these combinations, we can say that's x, z. No, not x. You don't like x. Y, z, etc. No. I will talk about two-dimensional field theory. Okay, I will. Okay. Maybe you're right. I will go to the next things. Okay, so indeed, this introduction was to say what I've been doing all this time. Now, let me just motivate you in 2 words why I'm interested in what I will speak about. So here in this integrable model, the spectral problem is essentially solved. That is, if we have a spin chain with length L, we know how to compute in principle all the spectra. And there is a method called, which is built on the traditional methods, Bethe Ansatz, Thermodynamical Bethe Ansatz, functional equations for the for the Q operators and T matrices. So this is called now this is called by the people who work on that quantum spectral curve. So this is essentially this is a Q system. This is a system of functional equations which allow to reconstruct a Riemann surface with and once we know this Riemann surface, well, at least we can expand it around the singular point. We know everything about the spectrum. So the spectrum of the excited states in this chain and the fields are defined by their charges, which describe the behavior of this Riemann surface at the singular point. So this is kind of quantum Riemann-Hilbert problem. So this is solved. So, yes, there are eight functions, which yes. You have 8. Yeah. Each component is yes, 8 functions. Yes. So, yes.
When you have some superposition of SU, you have 8 and quantum is a system of equation on this 8 and they can be solved. So the number of the it's number of solution of system. You have system is 8 functions.
Any function independent function is
in the same sense as the XXZ model has 2 degrees of freedom. In this, yes, 2 degrees of freedom, yes. Well, in this sense, no. Then, in this sense, you have two Q polynomials for XXZ, yes. Of course. So let's I continue. So the correlation functions in this model are something which is non-trivial, and in spite of the progress made in the last 9 years, still it's just in the beginning. So the typical correlation function for this problem is we have two spin chains, and they merge, and we have another spin chain. So we have one state here, psi 1. Space. The space of all possible states in all possible spin chains with length L. Space quantum space. Well, you have spin chain. The spin chain has states. So we have 2 spin chains, and they interact in some way, which is dictated by the original model. So we have to define this interaction, how so they can split and join. So there is non-trivial So you have a direct product of two states. Sorry, almost. Oh, yes, this becomes strings. This becomes strings in this high strong coupling limit. This spin chain describe the string states. Yes, and the strings can merge and which space?
You have picture on which space I picture. Line.
Ah, this is yeah, this is the evolution. So this is time. And so we have you can imagine that we have a two-dimensional model. So this is a world sheet. Yes. If you have spin chain, it evolves with
spin chain is running
time. I will explain that, or I will give you a review to read. But let us concentrate on the essential thing. This is just to explain the motivation. So this 3-point function can be computed in this way. So you cut this pair of funds into two sheets, and these are already disks. And you have some excitations from these spin chains here and others here. And also, in order to glue them back, we have to insert complete set of states, intermediate states here. Yes. So we glue this seam to this one, and some to the same. You just insert the identity operator, which is sum over states, along all these seams. So this partition function is obtained by these form factors, which are called hexagons. And what we have to do is to perform the sum over all these intermediate states. And this sum is not easy to do, because there is an interaction, and also so they can scatter, and we have phase factors and as matrices here. So we have to do very delicate cancellations in order to build to construct this sum. So we have to construct a cluster expansion for this. And this is a very non-trivial problem. People know how to do it up to second order. And so this is something which is not yet done. So we have to learn how to sum over these states. There is a problem. There is a method which has been developed long ago by Yang and Yang, the Thermodynamical Bethe Ansatz. So in that case, you have just one spin chain which evolves with time in this way, or if you you can consider it in the other channel. Instead of spin chain, I would prefer to speak about field theory, relativistic field theory, because in this case we have invariance, and you can look at them at it from this direction or from this. So this is either infinite systems which evolves at finite temperature, or a finite system for which we compute the ground state energy. And this problem is solved by Yang and Yang in 68, and this their solution was used by Alyosha Zamolodchikov in the about 90s. to compute the finite volume vacuum energies of this massive integrable field theories. But this the thermodynamic Bethe Ansatz, which was developed to study this system, is a thermodynamics. So it assumes that there are finite particle densities, which means that the number of particles is infinite. Thermodynamics. So the problem is, what is yes. And the TBA equation is the minimum. Yes, exactly. Yes. Exactly. Now you are interested in something more subtle. You want to build the statistical system which is behind the thermodynamical Bethe Ansatz. So this is the problem. This is what I will speak today about. Exactly, yes. So this statistical model, I promised to Hrach that I will start from the very beginning with the free boson and free fermion and display. This is more complicated than TBA. This is next level. But what we want to learn now is how to consider the simplest problem of cylinder topology, no pants, just no curvature, yes? And consider this the partition function for the TBA as a sum over objects, over some statistic, so this problem has been actually solved. It has been solved by Vadati and Kato and Vadati in about 85. So they defined the exact cluster expansion for the TBA. When after we finished our paper some 4 years ago, and Balázs Pozsgai told us about these references, which are not very well known, and I looked at them. It was impossible for me to read the papers, but I looked at the result, and the result was the same. So they did it. So for the free boson, this ensemble is the following. We have the sum over all possible loops. The partition function is all possible loops. And since the theory is free, this is exponent of a single loop. Yes, because they don't interact. Loops. Yes, good question. So consider, for example, the simplest possible topology, which is finite. Consider a torus with 2 cycles. One is of length L, and the other of length R. So let me describe it as a periodic rectangle, and Yes, so when R is very, very large, this is a cylinder, but we will keep R large but finite because we have to obtain well-defined expression. This is like a cutoff R. So the partition function of the free boson on this periodic rectangle, actually you can make it tilted. It works very well. I mean, almost the same formulas, but I won't go in these details. So the partition function of this free boson is sum over loops that are contractible. So this give a piece which is proportional to the area. But also there are loops which are like that, which go along one or the other cycle of the torus. So here they are like that, this, or another loop which goes this way, or a loop which goes this way and also this way. So it goes around the two cycles. So the ensemble of all these loops is the partition function is modular invariant.
How is the weight?
The weight is another good question. Yes, so formally, you have sum over exponent of minus mass times length. So these are the weights, but these weights are not well defined. You can define them in on a lattice. On a lattice, yes, but in the continuum, you have to do some effort to write this action in a more treatable way. And this work has done by Sasha Polyakov. So this is the Polyakov quantization prescription. So you introduce somehow internal and intrinsic and induced metrics, which coincide on the classical trajectories. Yes, so you can write the length in the, this is integral square root of determinant of the induced metric. Yes, and induced metric is, you have only one component, the x squared. So you like this times n, you like that at the integral with a new metric, which is G11 square root of G dx squared and plus square root of G G times n, and you integrate over the time. Now you integrate over this intrinsic metric, which is a second field. This is two-dimensional. So actually, it works for any dimensions, but we are interested in two. And then you have general covariance. This is theory of gravity, one-dimensional gravity, with m as a cosmological constant. So you have general covariance here, and you can put a gauge where this intrinsic metric is constant. And then the only variable here will be the proper time, the length of the interval. Yes, along the curve, yes. So let me write this, the final result. So the procedure is explained in Polyakov's book, Notes on Gauge Fields and Strings. So this is, let me first write the integral for a loop that goes from the point x1 to the point x2. So this is the integral from the proper time, on the proper time, from 0 to infinity. And so you can go to the phase space and integrate over the momenta. and then the integration over the non-constant modes of the momentum. No, sorry. Somehow the integrations over the momenta and x kills each other, because the integration of over the internal intermediate momentum, they are just delta function which impose x to be the derivative of x to be constant, to be 0. Yes, so x is no, to be constant, constant, yes. So yes, but you can integrate over the fluctuations, and what is left? Let me write. Krachik, I can explain you. And it is simple. It is simple. Okay. Let me explain you later, because we don't have time. Really, I can go cannot go to the interesting part. So what is left are the constant modes of the momentum and the coordinates, and this is the original action, but just one integration here. And the result, when you integrate over the time, you have integral I p delta x divided by p square plus p square, and this is the final propagator. So you cannot object. So this is if you want, you can take this expression and derive this from here. So now let us consider closed loop, contractible closed loop, and this is the integral is the same. But we have to integrate to divide by t. Why? Because we can use this formula, but this formula means that we take x2 is equal to x1 at one point, but we fix this point. So in order to undo this spinning, yes, but we have cut the loop at one point and introduced that the final and the initial point are the same. You have to undo this choice of the marked point. So we have to divide by the possibilities to do it, divide by t. So as a result, we obtain integral d square e d square e log and also we have I forgot to write. So we have 1/2 because we have two orientations of the loop, and we have to divide by this factor 1/2. And also we have the all positions of this point, P point, we can just sum over them. So this is the area of our torus. So we have to multiply by R times L. So this is the result for one contractible loop. This is one contractible loop. This is the path integral of one contractible loop. You agree? No. There is no x here because the integral over x is here. It's it's just a volume. Here, integral over p. Here, x is fixed, x1, x2. So it depends on the difference between x1 and x2. So now it doesn't because it's a closed. So next step is to compute a loop which is winding. There is the torus. So you do the following. You cut the loop at this point, and you introduce a discontinuity, which is just exponential of I momentum times x2 minus x1. Yes. And you just say this integral and introduce. So the result is integral d squared p L r divided by 2 log p square plus n square and exponent of I p times delta x. So this is a loop which has a discontinuity delta x. So delta x, in our case, we can consider loops that go around both cycles, but since one of the cycles is very large, there are no loop that goes around it. They have zero weight. So the only loops will go this way. So delta x will be some w integer times L 0. So that is, so our amplitude will depend on the winding number W through this exponential. Yes, this is the time component. So we have this on the torus. We have the torus is equal to, if we take x is equal to x1 plus I x2, the torus is the complex plane divided by the lattice of the periods. L is equal to L times z times integers times r z. So there is four possible integers. So we are interested only in loops winding in this direction. So this amplitude f w, the w is integer. This is a loop that on the plane it goes through w periods. Yes. So this amplitude is equal to integral d square p exponent of I p1 times w WL, yes, and log p squared plus n squared times RL divided by 2. Okay. So now I have to now we can here in this integral we can take in the integral over one of the components of the momentum, the second component, and we have you make the integral by parts, and then you take the residue. You obtain the integral dp1 exponent of minus mod absolute value of omega L P1, but when you take the integration by parts, you will have 1 over W, and WL, LR, and then you have here, you integrate over P2, yes, and then the residue will be at the point. This P1 is the first component of the moment. Yes. So this is P. Wait. No, it should be P2. Omega is a number. There is no scalar product. It will disappear because we. How disappear? What? You take the residue. Take the residue, then you have the I which appears in the P1 square plus P2 square is equal to M square, and the result contains I. With this I, it gives minus, okay? And modulus, absolute value, because we have to. Where? Here. But make take integration by parts. Then we will obtain this in the denominator. Yes. Okay. Yeah. So we have an expression for the loop amplitude for the winding loop, and remarkably, it is the same as if we take the wave function of asymptotic states in Minkowski theory, which depends on the momentum p, and which is on shell. E square minus p square is equal to m square, and which is point of I E. Sorry. So if you take C to imaginary value W L, then you will obtain this formula. So it's we have a wave function in the Minkowski theory. We continue it to Euclidean time, and you obtain this amplitude. So this can be used. This fact can be used to introduce the scattering, to use the scattering data in this statistical example, to introduce the interaction of loops via scattering data. So now we can take the sum of all these amplitudes for the free boson, and we obtain for the partition function, which is actually log of the partition function, is a sum over all loops, and we have to sum over all winding numbers. So 1/2 goes with the sum over positive and negative, and we have integral dp. Actually, let's do the standard parameterization. E is equal to m cosh rapidity theta, and P is equal to M sinh rapidity. So we parameterize this relation. Actually, this relation, because yeah. So we have the P times R, this volume which is left here, and the sum over all these rapidities with 1 over W gives logarithm of 1 minus exponent of minus L E of theta. This is P of theta. And yes, okay. So this is the partition function of the free boson on the cylinder. I derived it for you. I derived this for you. Of the free boson, one free boson, free bosonic field with phi Laplacian with this action. Yes. So now we will do something similar for the scattering theory for two-dimensional I don't need to. I have the exact answer. I don't need. Why? But why? I have the partition function. I have everything. No, but this was in order to compute the partition function in the limits when you have infinitely many particles. So this is the limit. This is the limit when L is when L is sufficiently small so that the statistically there is a big number of particles around winding the cylinder, and we have a finite density. If you have only one particle, if you take the expansion for large n, so we start with one particle, and this is not thermodynamics. But I don't need it because I have the exact answer. I don't need the thermodynamics. This is the answer. So what my goal is, if I have time to do that, is to formulate a statistical ensemble of loops which reproduces the partition function of interactive system. First, let me remind you. Yes. Yes. The torus is here because the cylinder is finite, and the length of the cylinder is the other cycle of the torus. If we take R going to infinity, then the partition function would be zero because the free energy is infinite. Now I take a system which is torus which is very long. So there is only loops that go this way, but not this way. And this is direction. This cycle is felt only by its length, which is this coefficient. For the complete system, also the answer is well known. And I can write it if you want. It's log Z for finite R and L is R minus R integral dp of theta log 1 minus minus integral, no, minus, not sure of then, dp of theta more large, okay. So there is a second term. So this is the finite volume vacuum energy of free boson. And this second integral describes the sum over the excited states of the free boson. So if you compute it by just looking at the discrete spectrum of the momenta, which is Pn is equal to 2 pi n divided by L, then you will have a partition function, which is the product of partition functions free oscillators. And you have exponent of minus En times R, yes, divided by 1 minus 1/2. And so this sum in the numerator is computed by this integral. Because I had no time to demonstrate it, but it can be just computed by multiplying this E of theta by a function which has poles exactly at the allowed momenta. And when you make integration by parts, you will obtain this expression. And here, this term, so for very large R, only this numerator survives. This is exponentially small in R. But when R is moderate, then this gives the contribution of the excited states of the oscillators. Yes, exponent of IRP. Sorry, excuse me. Yes, IRP is equal to 1. So P is quantized.
It's fantastic. What it has to do to chain, and in particular to this very in short.
This is the question which I would ask also, because I'm in a very I don't know much about that. I can explain. I can reformulate the TBA partition function only for scattering which is diagonal. Non-diagonal scattering means that, well, you can cheats by first diagonalize the scattering, use the nested Bethe Ansatz, and then writes the weights after that. But this is, well, not very satisfactory. So I cannot write it for the general case, unfortunately, only for diagonal scattering. Diagonal scattering, diagonal. Yes.
But you think that
of course.
The
yes. So you can for you I will just say that you have loops that interact. So at each crossing, you write if it is described by theta. I mean, this constant mode of the momentum is yes, interaction for these bosons, which is S theta minus theta prime. So each interaction is weighted by a scattering factor. Simplest example, the easy model. For the easy model, the scattering factor is -1. So this is the Dovichenko solution of the easy model. Sum over loops with -1 to the power of the intersections.
By introducing this, you can limit some objects which appear for
yeah, I can derive TVA. So this is the this field theory which you obtain. You do after that Hubbard-Stratonovich transformation. You introduce auxiliary field, and the effective field theory for this auxiliary field has as a mean field limit TBA. But we can show moreover, you can show that this theory is localized. So it's one loop exact. So you can the mean field result is exact. Oh no, this is the simplest possible case. Yes. Yes, you can derive. You can formulate. Yes. Yeah. You can formulate the loop gas for this chain, but you cannot. I don't know how to solve it right away. Yes.
Either the chain or any, I give you an algebra.
So so most generally, if you have a S matrix, S, A, B, C, D of theta prime, so you have a S matrix. This is the S matrix there. So for any loops that interact, you have A, quantum numbers A, B, and they can change to C and D. And then you have theta prime, and you put this weight to the interaction. You can do that, but then what? You have to diagonalize. You have to, I don't know how to apply this machinery. I will show maybe to this more general case. It would be great to do it. Oh no, this is field theory. This is field theory. This is field theory. So the spin chain can be considered as a field theory defined in some two-dimensional worldsheet, but this field theory is not Lorentz invariant. So instead of this simple rotation, you have a mirror transformation which exchanges time and space, And for this theory, it's more complicated. It's not just yes, yes. Mm-hmm. Oh, it's more difficult to consider scattering in the massless theory. It's more subtle, yes. Massive, yes. Oh, I can. Yes, this I can. Yeah. The massless limit is subtle, but it can be done. Then the left and right movers separate. Yes. For the massive case, yes. Okay, this is I don't know how much time. Huh? So the most non-trivial thing in the sum over loops okay. So then I will speak in pictures. So you have the cylinder, and you have loops that wrap the cylinder, and they can wrap it 1, 2, etc. times. So we introduce a factor, which is S of theta minus theta prime, with some S matrix that satisfies the usual axiom. And we want to compute the partition function of this loop gas with this weight. Important fact is that these loops, they don't scatter, because a second loop, if they cross this loop, it will, this crossing will be, because of the unitarity of that matrix, can be undone. And the weights of these loops, they're just product of weights of the single loops. So this is trivial. But the non-trivial thing is that the measure over the loops is non-trivial. So before we had this quantization of the momentum, which means that a loop that goes around the world like that takes a phase factor which is exponent of IPR, which should be equal to 1. Yes. And now when it goes through the world, it meets all the other loops that go around the cylinder, and we have a product of scattering factors which adds to the weight. So we have a quantization condition which is exponent of I R P of theta, and also product of J S of theta I minus theta J is equal to 1. So this is the quantization condition. This is the usual Bethe Ansatz. So now we can write this as exponent of phi I of theta 1, theta n. So this is the scattering phase, which is non-trivial. now the integration over the momenta actually should be replaced by the integration over the scattering phase, because this is the quantity which takes equidistant values. And so the measure for n lines, wrapping lines, the measure should be d phi 1 d phi n. So how you can describe that in terms of the integral over the rapidities, d theta 1, d theta n? Well, there is a Jacobian, and the Jacobian d phi I d theta j is called the Godin determinant. Pi is the scattering phase. It's the determinant of the derivatives is the what now we have to so our goal is to compute this Godin determinant for any configuration of ice in kind of convenient way. So we will introduce fields, bosons and fermions, which compute for us these determinants. Yes, effective fields, which will new fields, yes. So this means that these are like Hubbard-Stratonovich fields. When you have a complicated interaction, you disentangle the interaction by introducing new fields, which take the interaction to themselves, their two-point function. Yes. So as a result, you obtain loop gas, but which depends on the values of these fields. But you know how to compute the sum over the loops. This is like in the free boson. And then you obtain an effective function for these new fields. Well, for the F in this sense, it's for that. So let me write 5 minutes, or let me write the Godin determinants. It has the following form: delta ij minus sum over the derivative. Let me define this scattering kernel of theta is equal to 1 over I, the derivative of log S of theta. This is the standard scattering kernel. So K of theta I minus theta J, and minus K of theta K. It's theta I minus theta J. So this is the structure of the Godin determinant. Plus. K not equal. Here?
No, in the sum. In the sum. K not equal I. Sum by K not equal I.
I prefer to write it equal because it's cancelled by the rights. So this is the structure of the Godin determinant. And so this this term is very large. This is of order 1. So we have to, we need to expand on the series which contains these terms. And but the fact that this is large it makes the problem subtle. But we know a way to solve this problem, and this is given by the matrix tree theorem, which treats such matrices of this form. So if you, the sum over matrix elements on each line of this matrix is equal to this element. So let me, so I don't know what to do with this. Let me write the field theory expression for the Godin determinant. So the determinant of this matrix G is equal to products so let's define it this way. G ij is equal to delta ij and di minus k, simplified notations, k minus k ik minus k ij. Plus, sorry, thanks. So now we write this as di minus some k ik. No, sorry, di plus phi bar j plus psi bar j j times exponent of phi j. So expectation value, where we introduce two fields, phi bar, psi bar with correlators, phi bar j is equal to k ij, and also the same psi bar j is equal to the same j. So if you, I don't have time to it is about 5 lines, the proof of this relation. So these are Gaussian fields. The determinant of this Gij is the expectation value obtained by all weak contractions of these fields. Yes. Sorry? The rest? Yes, the rest is 0. Yes. Yes. No, but yes, 5 lines. But I don't have time now to do that. I will just state it. So this is the proof of the matrix 3 theorem. Matrix 3 theorem, which in the mathematical theory takes maybe 10 pages or more. The proof, yes. So when you expand these things, you obtain the following diagrams. You will obtain so you have a propagators ij, which is this kij, and you have vertices. So which are the vertices? You have as many phi fields as you can have. Yes, but you have only one phi bar. And also you have vertices for the Fermi field. So there are 2 Fermi fields, and you have also many phi, psi. So this is the bosonic propagator, and the fermionic. Let's draw it as a dotted line. So the same correlator, yes. This is important. So now let me draw a generic Feynman graph for this simple field theory. And it has the following form. There will be, and also there is a such vertices which comes for D. These elements for the. So we have these roots, yes, and we have propagators that go from them, etc., like trees. Yes, tree-like. Because of the structure of the action. And also, you will have loops. We have trees with cycles. So we have rootless animals and trees that pop up from them. And also you have fermionic loops you have to take them with minus sign, exactly the same picture, etc. And you see that the fermionic and the bosonic loops cancel because you have the same propagators here. And the result is that you obtain an ensemble of trees that cover all the endpoints of this, you consider, yes. So this is the matrix tree here. So now when we consider the grand ensemble of all such matrices, because you have to sum over all windings, then you can construct a very simple theory, perturbation theory, for these loops. So these trees, they symbolize actually ensembles of loops which are related by interactions, this case. And the interaction is such that you don't have loops, you have only tree structure. So you can just replace this cluster of loops by one single loop, but with modified weights. So the final result is the same as the free bosons or free fermions, but the weight will be different. And this weight, instead of the energy, L times energy, will be some function, pseudo energy, which is, it's called pseudo energy in the TBA literature. And it satisfies nonlinear integral equation, which is the equation for this ensemble of clusters, and which is the TBA equation. You can, of course, derive it as a Schwinger relation equation for this effective field theory. So, but I don't have time to talk about that. So, okay, that's it. Thanks.
Okay.
Will be a